Nuclear transmutation. You probably have heard about the alchemists in the Middle Ages. They sort of were chemists, alchemists. They were obsessed with trying to convert things into gold. Gold, very valuable element, and it's like if we could make something else into gold, we could be rich, right? And so it's like, let's see if we can make something that's really cheap and easy to find, like lead or iron or something, and change it into gold, and this would be really awesome. Well, they were not successful, although they did discover some very interesting things. Some of them involved urine. But they weren't successful because in a chemical reaction, you can't change one element into another element. In nuclear reactions, you can. One element can change into a different element. This is called transmutation. It occurs in radioactive decay, which is the natural decaying of radioactive nuclide. It happens in fission, where you're splitting atoms into smaller pieces, and it happens in fusion, where you're combining nuclei into larger ones. You can also have other nuclear reactions that result in transmutation. Here's a couple of examples. Here's nitrogen-14 plus helium-4 makes oxygen and hydrogen. Okay, these equations just don't match up with what we learned in balancing equations in Chem 1A, right? Nitrogen plus helium makes oxygen plus hydrogen. Yeah, that's weird. Aluminum plus helium makes phosphorus and a neutron. Very strange. Nuclear. In the 1930s, scientists started building accelerators. In order to cause some of these reactions to occur, you basically need to shoot small particles like alpha particles at nuclei and sort of smash them. You've probably heard of atom smashers. That's really what they're doing here. So there are different types of accelerators. A linear accelerator accelerates a charged particle in a line. So we get a charged particle in an evacuated tube, and it gets accelerated by a potential difference between the ends of the tubes. So if you have a positive charged particle, it will be attracted to a negative voltage, and so you can accelerate it that way. This is a picture of the, I'm not even going to try to say the name. One of those is a child of Marie and Pierre Curie. They won the Nobel Prize in 1935 for working on nuclear transmutation. It's like modern alchemy. Just over on the coast is the Stanford Linear Accelerator. And this is an aerial photograph of it. It's very long. This is a multistage linear accelerator, and it can accelerate particles up to 90% of the speed of light. That's really, really fast, right? When those particles at that speed collide with a target, they produce a shower of subatomic particles. I mean, you're literally smashing atoms into each other and looking at the fallout, the pieces that go flying. So in 1990, researchers at the Stanford Linear Accelerator got the Nobel Prize in Physics. They discovered that protons and neutrons are composed of smaller particles called quarks. So it turns out, I mean, yeah, we tell you about protons, neutrons, and electrons, right? And now we've also introduced this idea of the positron, the anti-electron. There's a whole host of other particles inside these particles, right? The deeper you dig into science, the stranger it gets, and the more you realize that you do not know. So I'm not going to test you on these subatomic particles, but just know that they exist. There's muons and pluons, and there's Higgs bosons, and there's all these just crazy, crazy things. And if you like that, you might want to get into particle physics. Most chemists are happy to just ignore that. Because isn't an atom small enough to worry about? Why do we have to worry about things that are smaller than protons? Anyway, the multistage linear accelerator. So this is the type that Stanford has. How does this work? A single stage, you're limited by, you've got this one tube, right? How long can you make an evacuated tube? Here we've got a series of tubes, and the tubes have increasing lengths. They're connected to an alternating voltage. So the particle gets repelled by the tube it's leaving and attracted to the next tube, and that gets repeated as the particles move through each tube. Obviously, this requires some timing, right? So the idea here is you've got a proton source. So you're shooting out some protons, and it enters this tube. As it enters and goes through this tube, we change the far side to negative so that the proton is attracted to that. As it leaves the tube, we change that side to positive so the proton is repelled. This is negative, it's attracted to the next tube, gets in there, we switch it again, and so we're accelerating it through each of these tubes. With each tube, it gets faster and faster and faster. And then here you have the target. Any questions? It's the very, very simplistic explanation. It's good enough. That's all we need to know. That's a linear accelerator. And then we have cyclotrons. Here we've got an alternating voltage that is applied between two semicircular halves. So the charged particle gets accelerated back and forth, while magnets cause it to move in a spiral path. It accelerates as it spirals outward and ultimately hits the target. So what do we have here? Here's one semicircle, and here's another semicircle. And so again, we're using alternating voltage and taking the proton source in the middle, and it's going to be spiraling out because of this alternating voltage, and it's going to get faster and faster and faster until smash, it hits the target. This is an aerial photograph of the Fermi National Accelerator Lab. That is 2 cyclotrons in a figure 8 configuration. Right? These things are big. I forget how long the Stanford one is, but you'd measure it more in like half a mile rather than in feet. So I asked Siri, she brought me to the website. The nuclear accelerator at Stanford is 2 miles long. That's a long building, right? And these you can see, from, those are buildings in there. These circles are really, really big. These are large facilities.